teething glitches. It is a new platform that we're also using and have been introduced to. So it is not the usual platforms that we use for learning. So we're all getting acquainted with it. And this is, as I said, a pilot study. So please do bear with us. You are welcome to put any comments or messages to me as we move through this presentation in the chat group. Would you like me to just quickly browse through the WaterNet online course content for you? Would you like that? Just very quickly before I start my actual introduction. Anybody can answer.
Yeah, I think that's fine.
Okay, good. All right, so I'm going to share my screen and I'm going to direct us to the WaterNet online course. My screen is going to be a little bit cluttered because I've got a few things open for you. But yeah, so from what I can see, if I visit Studio at WaterNet online, this is the sort of interface that I have. I think yours probably looks a little bit different. On the first page, the first section is the introductory video and reading material. So what we've put on here for you from an introductory video about the people that are and the aims of the course, I've got 3 readings that I put up for you to have already done yesterday. So the first reading I have is the state of hydrological services in developing countries. And this was a document that I put up for you because it really managed to capture some of the issues that we're having throughout the African continent and many other developing countries around the world. The second document that I've put out for you is called Observation Networks. It was done by the World Meteorological Organization in 2019. And this is a reading for you. It's actually a slideshow that's converted to PDF, where you will be able to go through and look at some of the information that they've gathered in terms of observation networks. Now, the reason I put these 2 up is the main sort of driver for us moving towards Earth observation, remote sensing, and satellite remote sensing Earth observation, for example, has been the decline in the services available to us in terms of hydrological networks. And we will talk a little bit about this when we move on to the presentation. So this reading gives us some background as to some of the major issues that we have in terms of actual physical measurements, ground-based measurements, and the contributing factors to the decline in observation networks. So this sets a nice background for us as we move forward. And the third reading that I've put in here for you is a review of Earth observation and remote sensing for water resources management in South Africa. And this was a major scoping study, that we did with the Water Research Commission of South Africa. We had several partners play a role from various universities, research institutes, etc., that came together and wrote up this review for water resources management, the role of Earth observation and where we see ourselves. So this was a decade ago. Now, 10 years on, we're not even halfway there. So these readings are just your background readings. So I'm gonna just show you the bottom. The bottom says Google Earth Engine, but you don't have anything published there yet. This is the content coming up in Thursday's live session. So Thursday's live session is going to be an extremely important one where we look at Google Earth Engine as a platform to access remote sensing data sets, satellite data, etc. So that's going to be a nice one for you. And if you want any sort of certificate from this course, you're going to have to make sure that you also do the tasks that are going to be uploaded for you. All right, so that's just a background of the page, the home studio page. I hope that you've accessed it. In the update section, you would have seen an update from me where I've asked you to register to Google Earth Engine. So I'm just going to urge you again, if you haven't, can you kindly do so today? It takes sometimes 24 to 48 hours for the registration to go through and be processed. So in order for you to have a good session on Thursday, please register on the Google Earth Engine site today. I've put it up under updates. You can have a look at that, and the site information is there for registration. The other thing maybe I should share with you very quickly is a quick view of the course outline. So this week, we've got the Introduction to Earth Observation for Hydrological Analysis. And we started off yesterday where we gave you some reading and introductory material as background. Today, I'm going to do an introduction to Earth observation and, some of the background information, what sensors are available, how we use these different things for hydrological analysis, and a little bit of a review of some of the products and satellites available. And towards the end of the presentation, I'm going to show you a very small study that we did looking at the use of within a water budget model, within a hydrological model. So that's just a little case study that and then at the end of the presentation, there's a small task for you to do. So this is week 1. Your readings will be posted up again by tomorrow morning on the Google Engine, and I urge you again to please sign up for that. Thursday morning, we'll have a practical demonstration of Google Earth Engine, and we will run that entire process through you and do some training in terms of how you download and access data sets. We're probably going to focus just on rainfall evapotranspiration for now, so that people can come out with some sort of concrete learning and image that they're able to download and process. And then you're going to have a little task to do as well, where you have to download a data set as part of an assignment. Week 2, we hand over to the group at USDM, and they're going to look at the GLDAS platform and data sets that are water budgeting. And they're going to be using the QGIS. So you'll have some quick training on QGIS. And then they're going to do data calculations and analysis on water budgets. So this is sort of a breakdown of what our next 2 weeks are going to comprise of. You will get more details about week 2 in terms of contact sessions shortly. So let me stop sharing. Okay, Maria, if you're still on, can you please turn off the mics of Nelson, Miranda, and Tagu? Thank you so much. All right. Okay, so I've got a message here from somebody. How can I access the course? You have to be invited and enrolled into the course. So unless you were invited and enrolled into the course, you will not be able to get access. If you have any other queries, I think Mariah Makopa is on this chat group. You can directly contact her about how you can, or directly message her via the Zoom meeting about how you can gain access if you are allowed to do so. All right, so let's move on to business. Where are we? There we are. I'm gonna turn off my video. I'm gonna be turning off my video so that I can give you a good big screen. All right, and we're gonna go move on to our slideshow. right, so again, at various points during this presentation, I will be looking at the chat group before I start a new section. So I will try and answer your questions as we go along. I would just like to say that, we are all learning. I believe everything in life is about lifelong learning. And yeah, so as we go along, if you have any lovely content to share with us, any comments, etc., please feel free to drop a comment and add value to the presentation and add value to this session. My role here is to talk about Earth observation for hydrological analysis, and I'm going to be focusing on just a basic introduction. I'm not going to teach you about what remote sensing is and the electromagnetic spectrum, but I'm going to direct you to something that you can read that will help you on that. I want to talk about space-based assets and the move to satellite-based remote sensing for various hydrological fluxes. And then I will focus a bit on rainfall, evaporation, soil moisture. We'll have a very brief chat about some of the vegetation mapping platforms that are available. And we'll talk about some of the challenges that we have working with remote sensing data sets. And I'm going to direct you to some readings about the future of Earth observation for hydrological analysis. And then I'm going to talk about a very small case study that we did where we took in satellite-based rainfall and we put it into a very complex hydrological model. And that was something that we thought that we would not ever be able to do, but we were eventually able to do it. And I want to talk about the results from that very small study. That's all I have time for at the moment. But yes, there's plenty of reading that you can go out and further, especially if you're looking at furthering your knowledge on the areas and the different sensors and how they work. And there's also plenty of information out there for you if you're a master's or PhD student looking for some direction and pointers in terms of your research. All right, so we all know that the demand for water is growing inexorably due to the population growth increase and its impact on food production, urbanization, climate variability, and climate change. And throughout the world, there is chit chat everywhere about how much of water we need, the fact that our water resources are dwindling, the fact that our water quality is poor, the fact that climate change is happening and we're not sure exactly how it's going to be affecting different areas. I mean, climate research scientists have been working for decades on climate projection models, etc., trying to quantify and predict what sort of changes we're expecting. I know, for example, in South Africa, we're expecting different things happening in the different regions. For example, some studies show that the KwaZulu-Natal area where I live in South Africa can expect more rainfall in our rainy seasons. And the Western Cape area is going to probably expect drier winters, for example, drier summers, for example. And yeah, so there's varying results put out there for varying countries around the world. And we're trying our best to try and identify what's going to happen, but there's so much of variability, there's so much of variations, and there's so much of uncertainty in what's going on. But there's no doubt that we need water. Water is vital. Access to water is vital, not only for drinking, but for ecology, for agriculture, for engineer, for industry, for sanitation, right? Just for us to survive on Earth, we need water. And there's a lot of pressure, not only on the hydrological community, but there's a lot of pressure throughout on various scientists in the multidisciplinary arena that we're working on in order for us to make water resources management decisions and adequately plan, manage, and predict the changes in water resources. So we have huge tasks ahead of us in terms of integrated water resources management, planning for the future, water security for the future. And we've got tasks ahead of us that we need a lot of information for. So water resources management decisions, we need data, we need models, we need to be able to justify, predict, and understand in order for us to make the pertinent decisions that we need to make. The models, the methods, whatever we're using, we need the data. And we don't just need data as in, I need this information and that information. We need good quality data in terms of both its length of data sets and in terms of the actual quality. You know, how sure are we that this data is actually good enough? Has it been validated? Has it been calibrated? So we need good amount of data sets. But what is the reality? The reality is that data collection has become more difficult, and there is such a huge decline in the observation networks as you've seen. Certain countries around the world, certain places in Europe, they're quite fortunate. They're actually closing down some of their stations, observation stations, and moving to alternate measurements. But in some instances, it's okay for them. For example, they don't have to worry too much of changes or variability. But the reality is, in most parts of the world, data collection is becoming so difficult because of the financial constraints. Governments just don't have enough money to contribute for maintenance, limited human resources, paying people, skills, people having the correct skill sets in order to collect the data, analyze the data, make sure it's error-free, maintaining data sets, for example, maintaining the equipment. Some of the measuring equipment costs millions of rands, and maintaining it is quite a problem. Accessibility. So we can't go and put in a lovely rain gauge station on every mountaintop. Accessibility is going to become a problem. Security. A lot of places are plagued with theft of systems. We put in hundreds of thousands of rands worth of equipment into a place, and it gets demolished and damaged, either for theft of batteries, for theft of the metal structures, etc. And these are some of the things and some of the realities that people face in terms of data collection. But the whole bottom line is there is a decrease in our observation networks, and it's becoming more and more difficult for us to access the data. And even where, for example, there is data sets available, for example, with the South African Weather Service and some other institutions that house data, it costs an arm and a leg. Really, it costs hundreds of thousands of rands, lots and lots of money for us to be able to access data. So we have lots of problems, and we look to the skies, we look up above, and we look to the skies to answer our prayers. All right, so that's where Earth observation comes into play. Earth observation, gathering information about the planet's physical, chemical, biological, ecological systems via remote sensing technologies, which are supplemented then by Earth surveying techniques encompassing the collection, analysis, and presentation of data sets. Earth observation technologies, for example, satellite-based monitoring, they can be very useful and very cost-effective means of replacing or complementing field data collection. I would be very reluctant to say completely replacing, but we have to be realistic. In certain areas, we just don't have the data, and we have to replace it with the Earth observation data that becomes available in those instances. It is, however, not the ideal. Some of the main benefits of Earth observation data are that it can provide coverage over large areas, remote areas as well, with systematic, repetitive data captures. Right, so we can rely on a continuous data set in most instances. However, there are lots of issues that we have even with Earth observation data sets, and we'll talk a little bit about them. Earth observation data can be integrated with field or remotely collected data. That is, it can be done together with real-time data observations and collections to produce effective, predictive, and analytical products. Earth observation includes more recent types of information. For example, we've got now drones, CubeSats, UAVs, the unmanned aerial vehicles, as tools and opportunities to add to our data collection at finer scales and to add to this entire technology that we have called Earth observation. Now, there's different ways. We have different types of sensors, different types of technologies that are available for us to gather this information. And you'll see as we go along and talk about some of the sensors, you will see that there's different systems that are put onto some of the satellites, for example, or the aerial aircrafts, which capture information about the Earth's surface in various ways. There are many, many studies that have been conducted, particularly over the past 2 decades. There's been a huge increase in the number of studies that have looked at the potential or the actual use of satellite-based Earth observations in hydrology, in hydrological analysis, in the sciences. And there are many different fluxes and state variables that have been looked at as a major focus of remote sensing and Earth observation. Land surface temperature, runoff, snow cover, water quality, elevation, land cover variables, surface roughness variables. All of this type of information can be remotely sensed. And there are many products that are available that are continuously being developed and further developed for this type of information. Important fluxes for us in the hydrological community, evapotranspiration, soil moisture, and precipitation, apart from the vegetation mapping, can also be estimated from remote sensing. And many of these are then subsequently incorporated into water budgets, either directly into mathematical calculations or into already developed hydrological models. And there's been a lot of work into looking at integrating and incorporating this type of information into hydrological models for improved modeling modeling output, and to add value to catchment level decision making, particularly in the context of integrated water resources management. So what exactly is remote sensing? What are orbits? What is the electromagnetic spectrum? As I said earlier on, I'm not going to be delving into the science of what remote sensing is, but I've got a slide here, which is the Earth Data website on the NASA platform. And there's a nice background page where they talk about remote sensing, orbits, how we observe with the electromagnetic spectrum, what are the sensors, what is the meaning of resolution, what are the data processing and interpretation analysis, etc. So please check out this site if you're new to this type of work, where you can get an excellent understanding of remote sensing in terms of its science. Let's go back to our space-based assets. In 2009, the Group on Earth Observation provided us with the space-based assets that they had in play. So these were some of the top satellites that were providing information on the Earth's climate, on different variables, to predict different biological characteristics, hydrological characteristics, ecological characteristics, and etc. So you'll find that there are different countries. For example, on the right-hand side, we've got Japan, Korea, China, India, with their different types of satellites. And then on the left-hand side, the USA satellites, and then the European Union, EU METSAT satellites here, and then combinations. So satellites that are housed by a combination of countries. For example, the TRIM here, is a joint operation by NASA and the Japan Space Science Association. Right, so this was 2009, and as we move on, space-based assets, according to the NASA Earth Sciences recent webpage, assets from 2020 and beyond, we can see that there's a large increase from the basic 10 to 12. We've easily got at least 20, and these are just the major ones, all right? So there's been a huge increase in space-based assets where millions and billions of rands have been put into launching up satellites into the atmosphere for various things. Some are there to gather information on space weather. Some are there to gather information on the Earth's climate, and some are there to gather information on the oceans, for example. GRACE is there for, that's this one here in the middle, the GRACE satellite, very important for altimetry. And yeah, so there's plenty of satellites that have been launched, and many of them have got their many of them are carrying on from their predecessors. So for example, you can see up at the top here, I've got Sentinel. So Sentinel started with Sentinel 1, 2, 3, and here 2020 to 2025, Sentinel 6A and B are being launched, right? So you can see that there's projection for the future here. And these are just the major ones. There are many CubeSats, and CubeSats are the smaller little satellites that are being put up into space. A lot of them being put up there by private companies doing work for environmental studies and research, etc. And that's also becoming quite popular right now. So they also add value to the bigger picture of space science. All right. So what are some of the things that we use all these space-based assets for in terms of hydrological analysis and water resources management? We can use the space-based information for land cover and land use mapping, for irrigation, for water use efficiencies, estimating the water use of different types of crops. So if you've got new crops coming in, for example, you want to plant more macadamia, you want to plant more avocado, you want to know how much of water cannabis is using, and you don't really want to grow a field of cannabis, you can actually do all of these things via remote sensing data sets as well. Slope stability mapping, DEMs, flood risk mapping is seeing huge amounts of interest. Just drought indices, flood risk mapping, inundation areas, snow extent mapping, wetland, water quality monitoring. There's lots and lots of new information coming out with the new Sentinel range as well. There's a lot of water quality monitoring, algal blooms, pollution source detections, water footprints, water accounting, hydrological modeling, drought indices, and the list goes on, right? So surface water, groundwater, runoff, these are the newer areas that are being looked at in terms of Earth observation for the different types of hydrological analyses. And all of these relate back to being able to apply in our integrated water resources management strategies. So these are just examples. So this is what a trim image looks like. This is a typical remotely sensed image, which comes off the TRIM site. So TRIM is a global coverage, and this is for a particular basin in China, thanks to Professor Wim Bastiaansen from WaterWatch, which I think is now ERIWatch. And he's provided me with a few slides here on some of the work that we did together with his group in various areas. So this is TRIM, this, for example, soil moisture from thermal data, And this is a typical soil moisture map that we can get directly out of remote sensing platforms. Land cover mapping, okay, we've got Landsat here, 30 meter, MODIS 250 meter, QuickBird 1 meter resolutions. So land cover mapping is another area that we can use our satellite information for. And then you can gather different types of satellite information, both rainfall and evaporation, for example, if you want to do drought monitoring. In this example, this is based solely on evapotranspiration. But if you want to use the SPI, for example, you can use precipitation. And you can do the SPI indices or calculate SPI indices directly from remote sensing data sets, from satellite remote sensing data sets. You can use SPEI, for example, directly and get your rainfall and evaporation from your satellite-based information. All right, so there are plenty of opportunities for the use of Earth observation in hydrological analysis, both in South Africa, because my research is based in South Africa, but also internationally and definitely on our continent. There's plenty of opportunity given the fact that we have such limited data resources available to us. And Earth observation is going to enable us to bring together the many different types of data sets that are available out there and integrate this into our hydrological models, our water budgets, our decision-making tools, so that we are able to move forward in our science. So there's a lot of potential for Earth observation, and there's a lot of research that's been done over the past, at least over the past 20 years, active and advancing research, but definitely over the past 40 years, lots and lots of research starting in this arena. However, and I can talk from a South African point of view in particular, there has been a lot of reluctance. So even though there are platforms that give us the Earth observation data sets, they make it freely available, there's a lot of reluctance in uptaking this into our methods and our models. We have been able to take the GIS platform and we've been able to bring in so many different types of information to visualize what is happening around us in terms of our different fluxes, rainfall, evaporation, soil moisture. Now we have the ability and the tools to be able to sense data from out of space and gather information to bring back here to Earth and be able to interrogate this information and combine this information with the actual measurements. However, there are lots of issues, skills required. A lot of people just hear the word remote sensing, satellite-based, and they start to fright, right? They feel that it could be too much. It's going to make our models more complex. It's going to become too data intensive. And yes, that's true. It can become more data intensive. And when we first started working with remote sensing data sets, I can remember in around 2008 or so, it was quite a schlep to be able to bring in a data set and then go through one set of platforms to do one type of analysis, then kind of bring it into another platform to do another type of analysis, and then finally bring it into ArcView or Arc at that time to be able to view the imagery. So now there are so many different platforms. We've got the whole Internet of Things behind us. We have cloud storage, we have high supercomputing centers, and we have people in different parts of the world that are committed to bringing us the data. So we are so fortunate in that we have people out there that are making things open source and bringing us the technology to bring the innovation into our science and to bring innovation into water resources management using space-based assets. So this slide is just an example of some of the tools that we can use and where we can bring in our EO data for water resources management in terms of water budgets and hydrological modeling. All right, so let's move on into the next part. And this is where we start talking about some of the sensors. So I'm going to list some of the sensors here. I'm not going to give you too much of information on them, but I want to introduce you. This is an introduction. So I wanted to introduce you to some of the sensors and some of the technologies that are out there. And I'm going to show you some of these sites so that you're able to go in there and have a look at them for yourself. For some of you, maybe you already know some of this information, but this is just an introductory course. So I'm doing my duty to those who don't know too much about what's available and how to access it. All right, so the Tropical Rainfall Measuring Mission, one of the longest running rainfall based sensors, was launched in around 1997. And it was responsible for many, many research breakthroughs in terms of being able to take readings from satellites that are based out there, millions of kilometers away, and bring them to us on our computer to estimate rainfall in various parts of the globe. So this is a global product. It's got a precipitation radar, it's got a passive microwave and visible and infrared scanner on it. And it was running right up until around 2014 or so. And then it started to slowly die off, but brought lots and lots of information and work to us, and many beautiful products that many people rely on. But TRIM lives on, because TRIM then GPM then succeeded TRIM, and we'll talk a little bit about what happened with the TRIM data thereafter. So GPM is the Global Precipitation Measurement Mission. And this is also, again, an international network of satellites that provide global observation of rain and snow. Launched in around 2014, TRIM went on to about 2014, 2015, and slowly started dying off. But the whole mission of GPM is to build on the successes of TRIM. And GPM was initiated again by NASA and the Japan Aerospace Exploration Agency, which we call JAXA. And because these are the two major space associations that drove the entire TRIM project. But with GPM, there have been other people that have been included, other space agencies, the Indian Space Agency, the NOAA has been included, and EUMETSAT has also been included. That's the European Union station. So this is what GPM looks like. What's happened is that it's got both a microwave imager and dual frequency radar. So that's the KUPR and the KAPR. Those are the different bands. And before May 2018, the bands were measuring at different widths. So it was KAPR here was only at 120, but after May 2018, both of them are now measuring a swath of 245 kilometers. So this is what the GPM satellite looks up in space. I'm going to show you a website just now at the end of this presentation, and I'm going to direct you to the websites where this information is available to you. So you can go on, you can register, and you can go onto the NASA website, and you just look up GPM datasets, and you will be able to register yourself and download or request access for certain datasets. All right, so that's the traditional way of doing it. On Thursday, you're going to learn how to use the Google Earth platform and be able to access data sets that have already been preloaded for you for your use. So that's going to be lots of time solved and lots of problem solved, especially sort of lots of time reduced and lots of problem solved in terms of actually acquiring remote sensing data. What's happened is that there's also the iMerge product, where 2 decades of global precipitation data has been brought together. The iMerge is the integrated multi-satellite retrievals for GPM. It's an algorithm that combines information from whichever constellation of satellites are operating around the Earth at a given time to estimate precipitation over the majority of the Earth's surface. It's also been able to fuse some of the information and data sets between 2000 and 2014 while TRIM was still operational. So it's sort of a continuation of TRIM in that we had 1997 right up until about 2014. And then from 2000 to 2014, we've got a combined version of iMerge, which combines the GPM and the TRIM, giving us a nice long data set. And hydrological models and water budgets need a long data set, especially for rainfall, right? So rainfall is the driver of the hydrological cycle. And if you get 90% of the rainfall component correct, you A for away in terms of your predictions using your water budgets or your hydrological models. Version 6 release of iMerge is what I was talking about just now. This is the one that's fused the TRIM with the recent precipitation estimates, giving us a nice data set. The next one that I'm going to briefly talk about is the Fuse RFE. There's also a Fuse ARC. This is also a NOAA product, operated since 2001, and has a lot of modernization in terms of its merging techniques, reduction in error, bias, and improved accuracy, speed, and portability. The special sensor is a microwave imager similar to the one that's on the GPM, except that the GPM one is just far more advanced. It also includes infrared cloud top temperatures in it. Output resolution is 0.1 of a degree. It's a daily data set that's available. And there's a site that I'm going to direct you to, which is the Fuse RFE site. And this one is particularly for the African continent. So there's lots of beautiful information available to us from the Fuse RFE. There's also the Fuse ARC, which is from 2005 onwards, and it's based on the Fuse RFE information. This is now sub-daily, so it's 3-hourly technique of IR temperatures. It has also brought a lot of good information available to us in terms of what we want to do. Fuse stands for the Famine Early Warning System, and this whole product was released particularly for drought prediction in Africa. So I'm going to show you that site just now. NOAA has got the CMorph, which is the Climate Prediction Center morphing method. And this is a satellite rainfall product that's also available since 2002. It uses microwave rainfall algorithms along with motion vectors from infrared data, and there's a variety of sources that it brings together to create its data set. It's quite a flexible way in which the precipitation is estimated, and it's seen a lot of interest in terms of research. But if you look at the overall picture, the TRIM GPM or the TRIM original would be probably the major satellite-based rainfall product that's used throughout the world, and has the most support, and people have found that it's it works well, So a lot of the studies have shown that it is a reliable data set to use. TAMSAT is the last one that I'm going to talk about, and TAMSAT is the tropical application of meteorology using satellite data and ground-based observations. This product is by EUMETSAT, and it is actually has been developed at the University of Reading, and I will show you the website as well where we can gather the TAMSAT information. So we have daily rainfall estimates for all of Africa at a 4-kilometer resolution from 1983 to the delayed present. So when I looked a few days ago, I think the last was the end of October 2021, and they will shortly release by today, actually, by the 15th of the month, of the new month, they start releasing the previous, the first week of the month's information. It's starting to get a lot of recognition because it has now a longer data set available to it. It's been continuously worked upon and researched by the group at University of Reading and by different researchers at the Center for Ecology and Hydrology in the UK. And so this is what a rainfall estimate or a rainfall map looks like from TAMSAT. So this is 2021, month 11, Pentad 2. So they're just different. So you can source this information. I'm going to show you the website just now as well, where you can go and download the TAMSAT information. If you go beyond a certain period, you actually have to request the data sets, you have to register and things like that. As with most of the sites that provide you with satellite information, you have to register on the sites and you have to download or request downloads if they are not available on the Google Earth platform. Some of the rainfall sites require special tools. So previously, if you wanted trim, there were about 2 different ways. You could use the TOVIS platform, which is on the NASA platform, and you register up there, and that was the way in which you download your satellite rainfall. But now there are more modified ways of doing it, and you'll be introduced to the different catalogs on Google Earth Engine where you can access different types of information. So that's just made things so much easier. All right, so this is just a quick example of some of the satellite-based rainfall products that are available, or the sensors that are contributing towards satellite-based rainfall from various parts of the world. We've spoken about some of these things already, and some of the findings. So having reviewed a lot of the products and having reviewed very many case studies on satellite-based rainfall, etc., it seems like the accuracy of these products depends on the topography. It depends on the validation ground-based network that is available for validating these products. And it also depends on the types of bias correction techniques that you need to use. So there's a move and a need in a lot of these studies. It's found that maybe downscaling the data sets, with the ground-based measurements, but ideally some sort of blended rainfall products are the way to go. So the actual rain gauges still play a major role in able to use these satellite products effectively, particularly for rainfall. So yes, the satellite products are there, and they are a tool. They're an information set. They're available for us to use in many instances, but we still do require validation, calibration in certain instances. We still do require bias correction. And an ideal would be to be able to blend your radar, satellite, and your ground-based measurements so that you can, rely on one or the other in times where you have missing data sets, etc. And I think that's something that you'll see also comes up for future research, is how do we move forward in these arenas. So that covers what I was saying there. The next thing that we're going to quickly look through will be remote sensing for evapotranspiration. And there's no doubt that there's been a lot of work in terms of measuring ET, observation networks, the different methods, the different instrumentation that are used to measure ET at varying spatial scales, from your surface renewal techniques to your different methods of Penman Monteith and the various equations, etc., that we would do, Richards and Lineker, etc. But there has also been lots of work that's gone around looking at the way in which we can use temperature and land surface reflectances, albedo, etc., in order to estimate evapotranspiration. And there have been at least 4 major contributions to this type of work. And all of these have focused on using an energy balance system with satellite-based input products. And probably the most popular of the lot in terms of its open source nature, in terms of its, it's quite easy to use, it's easy to learn, it's available, there's a lot of support for it, would be the SEB system, developed by Professor Bob Su in 2002. And the SEB system is freely available, open source, available on the ILWIS platform, and now some other ways to actually download and use it. You can use it via MATLAB as well. There's a variety of input spectral reflectance and radiance bands, and you can use different platforms for that. So MODIS, Astameris, Landsat 7 and 8 are a combination of those two. Sentinel can't use directly, but there have been methods developed to get the thermal bands estimated in a different way and then incorporate some Sentinel information as well. So that's the different sources that you can use to get into your satellite information to eventually model your surface energy balance. And I will, anyone interested in this can just Google SEBS, Professor Bob Su, 2002, and there are some references here at the bottom that will be the major contributors to ET estimation. CBEL, metric, ET-look are the examples of satellite-based remote sensing derived evapotranspiration. And a major one would be the MODIS platform. So MODIS has its own ET product called Mod 16. It's a global data set that's available now at from 1 kilometer. It is now available at 500 meter resolution. So this is an example of MODIS ET data. It's a global 8-day, that's the Mod 16, and you also get an annual Mod 16A3 coverage, and now brought down to a 500 meter resolution from a 1 kilometer. Its MODIS sensor is aboard the Acura and Terra platforms. So MODIS is quite a popular ET product. It's also based on the logic of the Penman Monteith equation, and it uses daily meteorological reanalysis data. So reanalysis data will be a combination of data from observations as well, and an 8-day remotely sensed vegetation property dynamics from MODIS as input. So yeah, depending on what exactly is being used, there'll be variables of Penman Monteith that will be derived from remote sensing information together with meteorological reanalysis data provides us with the Mod 16 product. Mod 16 website, I will briefly show that to you, but it's listed here at the bottom as my reference as well, if you want to visit that and if you haven't seen that yet. So if you're looking for very quick access to ET information, you can go directly to the MODIS site and request data, download data for different, global 8-day versus annual, etc., for different years. And it is still operational and continuously updated. So it's quite a good product, and I'm interested to see how the change from the 1 kilometer to the 0.5 kilometer will affect the ET results. So it'll be nice to do a comparative study of that as we move forward. So that's a nice honors topic for one of my new students coming in next year. All right, this is an example of, for example, water watch. So this is a seabell generated image of the high basin annual ET. So this is what a typical evapotranspiration image would look like. Obviously, there would be a key here telling us what the different colors mean. How do we use this? So this is an example where we use the ET information in irrigation and water use back calculations, and you can see the different vegetation here, probably different growth stages as well, and how the evaporation is actually different over the different areas, and how we can actually distinguish the bare soil here as well. This is just an example of a small study that we did between December, a 6-month period where we had some good surface renewal information, and we compared it to MODIS ET information. So that's just a plot of the MODIS ET picking up the variations quite nicely, and a lot of good results came out of this short period data set. Yeah, so this is some types of comparisons that one could do with this type of work. So the last major thing that we're going to talk about in terms of satellite information for hydrological analysis in terms of this introductory level module would be soil moisture. So we know that typically soil moisture measurement is digging in the ground. So they are ground-based measurements. We have to put in probes. We have to put in different measurement components, TDR, watermark sensors, different depths that we're measuring at, and it's hands-on work. However, there have been a lot of research going on and a lot of modernization into a lot of the techniques, and we have now different ways of being able to upscale the footprint of soil moisture estimation. So one new innovative method that I can think of is the cosmic ray probe. So this gives us a little bit wider footprint instead of digging a hole in one place and getting soil moisture at that place at different depths. The cosmic ray probe is able to cover a wider footprint. And then we have land surface models as well, where we use a combination of models and ground-based measurements to predict our soil moisture or our indices. And finally, remote sensing. So there's been a lot of, especially in the past 10 years or so, a lot of work going into soil moisture measurement from remote sensing data sets or satellite-based soil moisture measurements. And this has been, particularly interesting because it moves away from the point measurement to a more, a wider spatial scale. Essentially, remote sensing of soil moisture, some of the techniques are the thermal infrared, near infrared, gamma radiation, and microwave, both active and passive. And it seems like the microwave, active and passive, is probably the most promising, techniques with the sensors and images that I use there, most promising in terms of soil moisture estimation. And I'm going to talk about one or two of the popular products that we have. So AMSRI and SMOS. AMSRI is the Advanced Microwave Scanning Radiometer. SMOS is the Soil Moisture and Ocean Salinity We also have the ECV and the CCI products. Recently, a lot of interest in SMAP. So SMAP's gained a lot of global interest in terms of soil moisture estimation, and SMOPs as well. So these are some of the soil moisture estimation techniques, products that are available. We also have models that can, this is one of the models, the pie top copy model that takes in, it's a rainfall runoff model. So it takes in meteorological and remote sensing data, and you're able to produce soil moisture estimates at 3-hourly intervals. And this has also gained a lot of interest in South Africa. And through the Water Research Commission, projects were commissioned where we could put this information out on platforms for specific research purposes. So this is an example of the SMOS. And very importantly here at the top, I've got a little diagram which says ease at which the product was acquired and processed, because I think this is one of the most challenging parts. I found SMOS to be quite difficult initially, but there are ways and means around it. And Spanish people have been extremely helpful in terms of providing support for that. The AMSRI and the SAG were much better. And now that we have platforms like GLDAS and Google Earth Engine, obviously the acquisition of remote sensing imagery has become, more and more important. So this is a typical image of a SMOS coverage. And if I had to draw out, or for my boundary area, this is what the soil moisture index would sort of look at. So this is a typical SMOS. This is a typical global product for AMSRI, and then you would go and cut and put in your boundary, and clip out the information. In this picture here, what I was highlighting is some of the missing data. So missing data is an issue even with satellite products, and there are ways and means of actually trying to overcome this type of problem. Cloud cover and various things contribute to the missing data sets, and you have to find means to create a continuous data set. This is one of the SMAP products. So this is SMAP 9-kilometer product. It's a 3-day composite soil moisture. So you can get SMAP for different time periods, and it's available on the SMAP website via the NASA global data set. And I'll direct you to that page just now at the end of this. Finally, I want to talk about some very important satellites that have gone up. And since 1972, the Landsat missions have been instrumental in us being able to move forward in Earth observation and GIS for different types of applications, both in multidisciplinary applications. And, being able to map vegetation and map areas, to be able to classify your areas via satellite remote sensing, to be able to do your vegetation mapping, your classification, urbanization, urban zones, etc., for all parts of the world, has been an immense contribution to science. So the Landsat missions, very importantly, have been able to, really bind together the multidisciplinary scientific community in terms of the data that it's made available to us. And Landsat 8 is the more recent one. Landsat 7 and 8 are still operational. They both work on a 16-day cycle, so you can actually, but they're alternating, so you can get a Landsat 7-8 combination every 8 days, so to say, which has been a huge contribution to the type of work that we do. And then the last one would be the EUMETSAT Sentinel. I mean, everybody has heard of the word Sentinel, Copernicus, etc. That's the European Space Agency EUMETSAT group of satellites, and Sentinel as well has been providing lots and lots of information to the different scientific communities. We're right up until Sentinel 5, 6 at the moment. Sentinel 3 has been a major contributor, particularly for ocean mapping, salinity, and things like that. And it's being looked at in terms of its finer resolutions. It's been looked at for evapotranspiration as well. However, there have to be modifications done and thermal bands not being present. So there's nice areas for research there as well. So Sentinel, one of the major contributors as well. All right, so I'm going to take a very quick break. So we've been on for like almost an hour and a bit. And I want to... Okay, so Mariah says, okay, so before we log off and before the session closes, guys, I would like, guys and girls, I would like for you to please turn on your cameras so that we can take a picture of all the participants for our admin purposes. So please remind me to do that at the end of this. And I would like to suggest a 2-minute leg break. So I'm going to turn off for 2 minutes. You can gather your thoughts, and if you have any questions, post them on the chat, and I shall be back in 2 minutes so that we can continue our conversation and look at a small application study of using satellite information in quite a complex, detailed white box types of modeling system, the Acura hydrological modeling system. Right, so back in 2 minutes. Before we start the next section, I think that I should direct you to some of those sites that we were talking about. So this, for example, is the TAMSAT information. So you can get some information from this group from the University of Hamburg. And this is the tamsat.org.uk website where you can actually download the TAMSAT data sets. I think that there is a registration process here, and depending on what type of information you require and how much of information you require your actual data set, you may have to do a requisition for that. This is an example of the EUMETSAT webpage and all the different satellites that they have available in their series. This is GPM. So this is the GPM site that's hosted by NASA. And you can get both the TRIM, you can get TRIM and GPM out of this. There's a data directory and also there's policies around it. So you have to register and then request for certain types of data, and some is available for you to download directly. Okay, sorry, that's just the group on Earth observation. This is the site that I was telling you about, unearthdata.nasa.gov. So this is also an open access, open science learning site. And there's some nice information here on what remote sensing is, what are the polar orbiting satellites, for example, what is the electromagnetic spectrum, and what are the satellites actually doing. Here, the spectral signatures of the different features and how they're visible. This is a nice example here of the different materials and their reflectances. Then there's some information about active and passive sensors and understanding resolutions. So this is a very nice site to give you some introductory information on remote sensing as a science, right? So what does remote sensing actually mean? This is the FuseNet data center. So as promised, I would show you the FuseNet site. In our slides, we also have the FuseNet site there for you. So yeah, don't forget that one. If you're looking for information, this is the USGS, USAID. So they actually provide the funding for the FuseNet data portal. This is MODIS. So this is the main site to get MODIS information. That's just the MODIS ET in particular, but you get, see, MODIS atmosphere, land, ocean, and then some information, the calibration. So those are the different products that are available. Under atmosphere, you get a whole group or a listing of products that are available. Under land, there's a whole listing of information available as well. Soil moisture, so this is the SMAP site and how you gather the SMAP product. This is a list of the SMAP products, for example. And again, here you have to register to get onto it. This is just the main NASA site, sorry. This is the main EU Met site. Oh, this is an active one. So this, for example, is looking at precipitation rates as well as, I think it's daily accumulated surface temperatures, right? So this is active, yeah, information. So you can actively go into this EU Met site and see what's happening in real time. And where was the last one? Okay, and so these are the some information on Landsat. So those are the major sites that I wanted you to look through. There's information available there for you. Let's get back to our slideshow. All right, so I'm going to spend the last 5 minutes or so of this presentation, and I'm going to show you a little study that we did in the Inca Marti catchment. So the Inca Marti catchment as a catchment that's in the very popular Kruger National Park area. The Inca Marti catchment, the catchment that we were looking at was actually the CARP subcatchment within the Inca Marti catchment. So this was just a very quick preliminary investigation where we were testing some of the satellite rainfall products that were available. And most importantly, we just wanted to see what happens with the Acura model. You know, the Acura model is a daily hydrological model. You can see it has different types of input, and it's actually very widely used in South Africa by several specialists and has gained a lot of popularity. I think one of the most popular things that have come out of our Center for Water Resources Research or hydrology at UKZN would probably be the SCS-SA model and the Acura agro-hydrological model. And this has seen lots of work being done internationally as well, and modifications internationally. So I used a research version of the Acura Hydrological model where I wanted to try and incorporate some satellite information into it. And okay, we've been through that. So what type of satellite information did I use? So I took in the new high resolution Spot 5 satellite imagery together with a company called GeoTerra Image. We did some processing and we were able to improve the classification, land cover classifications over the area compared to the national land cover database that we have. So that was the one type of high resolution satellite imagery that was used so that we could configure the model in quite a detailed way. So this is the carp catchment, for example, and we were looking at one of the sub-catchments, X23A. So that's up the top here, right? So that's the area that we were focusing on. This is just some of the vegetation and soils information. And this is an example of the configuration of the sub-catchment. So I split it up into HRUs, so hydrological research units. The HRUs were modeled into the dam, which was a node, and then the nodes link up together to the output of the, to the outlet of the catchment. So this was just a basic configuration. I simplified it quite a bit so that we could, really test whether the satellite rainfall was making a difference in, or even was, used correctly first, and then making a difference in terms of our water budget. So the Acura model is a rainfall runoff model, and as I said earlier, getting the rainfall right is the first and most important step, particularly on a rainfall-driven hydrological model. So what I did for the rainfall data from the rain gauge network was obtained from the Agricultural Research Council for different points in the catchment. And it was a short study time, right? September 2016 to September 2013. Sorry, September 2006 to 2013. And what I did was I first worked with the TRIM product, the 3B42 version 7 of daily rainfall estimates. And at this instance, Google Earth Engine was not available to me, and I had to go the long winded route of using TOVAS and several conversions thereafter, and finally to get it to a GeoTIFF to bring into ArcGIS 9. I then overlaid the TRIM imagery to the carp sub-catchment, and I had to do this sort of manually. And we then had to do point to pixel evaluations, and then created a record of the satellite-based rainfall for each of the sub-catchments. The Acura model climate files were then set up, and I used up-to-date temperature from the Agricultural Research Council's met stations at the site. All right, so this is what the TRIM data set over the catchment looked at. So there's a different pixels that were over the catchment. And this is what some of the data set looked like. So for a short 6-month period that we looked at, comparison of the actual rain gauge in the catchment to the satellite rain. I think that did really well. This was just some of the stats and comparisons, observed versus simulated. So this is the stream flow that we got out of the model. And you can see that the modeled stream flow, which is the simulated stream flow here, is compares actually quite well and is able to capture the observed stream flow quite well in this catchment for this time period. So we were relatively happy with this initial preliminary investigation. And afterwards, yeah, I managed to get a student, and we're working on bringing in, larger data sets. Sorry, I just need to move the screen along a little bit. Okay, so those are some of the comparisons that we had using satellite information, the rain gauge, and the observed stream flow. And we can see that, again, the simulated stream flow from the Acura model compared quite well with the observed stream flow. And yeah, the simulated stream flow using the rain gauge, in one instance here around the 3rd of January, it was a bit off. But the model takes a while to kick in, I would say, especially when depends on when the modeling kickstarts. So it depends on the antecedent soil moisture conditions. But as we went on, I see here, there was a better correlation, it seems. So those were just some of the initial things that we're playing around with and trying to do. We've subsequently been able to create much larger data sets, and current research is looking at larger data sets using bias correction techniques to correct the satellite rainfall before we put it into the model, and looking at comparative studies with that. So what were some of the challenges? And these challenges are not just with this little study that we did, but in general, some of the challenges that have come out of a lot of the research that's been done, where we're incorporating remote sensing data sets into models and hydrological modeling, or for water budgets, for example. There are, there's a lot of work to be done. So especially in operational hydrological modeling, if we are looking at large-scale complex models and we want to bring in satellite information, and not just one type of satellite information, but multiple products, there are lots of challenges with working with this. Integration of the satellite data sets into the hydrological model often poses a challenge, because you can't just directly bring in the satellite information. It depends on what format they are. And if it depends, it's a spatial estimate. And if your model is using point estimates, then you're going to have to do point to pixel translations in order to get the values at the pixel that you're looking at. Or you're going to have to change some of the way in which the model is structured so that it now becomes more spatially explicit. So you modeling not at a point, but you're modeling at a catchment area, and how you bring in that change into your model, and how your variables then need to be adapted, or your indices need to be adapted for that. So it's not very often that you just take data sets and put them into an already operational hydrological model. There has to be some sort of adaptation. And I think that's where a lot of reluctance comes in, is people don't want to really do that. And especially, for example, in consultancies, etc., where they want quick answers, and they want information, at the tip of their hands. Nobody wants to now go and try something different and try something new. I actually had a consulting, a little project to do recently. And when I was talking to the consulting engineers, and I said to them, they said to me, oh, we have a major problem. We don't have rainfall in this area. And I said, oh, that's not a major problem. I can just download the satellite rainfall data, and there's 2 different types, and I can show you what the model does with both of them. And they said, oh no, I'm not sure if our client's going to be happy with that. So yeah, it's not just being able to do it, but also to get the buy-in from the people on the ground, the people using the information, the people needing the information as well. So yeah, there has to be a lot of buy-in in terms of adaptation of not only the models, but even the scientists and the people and the consulting engineers and the stakeholders, and getting them to understand that this is the way in which science and technology is moving. Some of the challenges with working remote sensing data sets for operational catchment modeling, especially large-scale complex models, there's a lot of difficulties that come into source. You know, sometimes you register, you request data, there's long waiting periods. And I think that's where the GLDAS and the Google Earth engine that you're going to learn about soon really took a whole load off our shoulders, in that we were able to, with a few lines of code and a few simple instructions, we were able to get information in bulk, get our data sets, and we were able to quickly move on. And you're going to see that when you meet Shaden on Thursday. I found that working with some of the data sets, they have different frameworks, they have different tools to download the data sets, etc. And then also, they don't come in the same format. There's a lot of conversions that need to happen. And I think that's where Google Earth Engine really comes to play, in that we're able to get everything in the format that you require. And it just saves time and energy, and you're able to focus on the real science involved. I found that, it's a lot of scientists are reluctant to move forward in these innovative ways. And yes, the ground-based measurements, the observations, they have to be there. They have a vital role, but we have to look forward and we have to move forward. You have to have the expertise and the understanding. And I'll repeat what I said at the beginning. Life is about lifelong learning. So we as scientists, as we grow in our fields, we have to learn and adapt and incorporate new technologies in our way forward. I mean, who would have thought that 20 years ago or 25 years ago that every single one of us would have a smartphone in our pocket, like a mini computer where we can chat to people overseas as if we're sitting in the same room. So we have to embrace all of these technologies, even in the hydrological sciences, to better facilitate the type of work that we do. Supercomputing, the amount of cloud storage, spaces, treasure, those sort of things are always going to be there. Remote sensing imagery use up a lot of storage space, a lot of disk space, but housing them up in cloud storage has made things so much easier. And I think moving forward, that's going to become an issue of the past. It does take a lot of data to download. So if you have bad internet and things like that, you can battle it out. It'll take a while for your downloads to happen. But I think with the move to fiber and all of the new nice technologies available, we probably will overcome that problem quite soon. Not every one of us is able to own a supercomputer to do all this lovely processing. So yeah, we need to be able to have good computers where we can actually process information adequately for the tasks that we have at hand. The availability of good quality observed data, appropriate lengths, error-free, that is invaluable. There's no way that observed data can in any way completely be gone. It is vital, it is required to validate, to calibrate, to use in merged products so that we can get the best out of the satellite remote sensing information that we have. It also points towards blending our satellite and rain gauge information and improvements. So even though the satellite information is there, there's now techniques coming for bias correction, downscaling of your information, improving spatial and temporal resolution. So that's where the focus will be on improvements. There are lots of areas where they can become more improvements for satellite information, like water quality, groundwater estimation, for example. There's huge potential and amounts of interest and research that can go on in those areas to better understand the entire hydrological cycle and to get a better water budget, for example. So there's lots of information that that is out there, but we need both types. We need the Earth observation definitely, and we still need our ground-based measurements as well. As we move into this era, we have to look at more blended data sets. And I think going forward, there are lots of people throughout the world that have, come together and sort of moved along the same lines in terms of understanding the need for both types of information. All right, so I end off with my picture here from the group on Earth observation. I did pass through that website before. They have lots of nice information on activities in Earth observation. You can join up for free. And I love this picture where they bring together all of the different types of in situ measurements. And as I said, these are invaluable as we move into the space era and new innovations in hydrological analysis. All right, so that's that. I'm going to stop there. And that is the end of my introductory presentation. And I'm happy to answer questions. So I've got a question here from Peter. Thank you, Peter. I haven't finished my PhD yet, hey, so I'm not doctor yet. I'm getting there. As I said before, I went into management before I decided to pursue a PhD, and I've got a PhD in motherhood. So I've got 2 children that I have to look after. Right, so I see a lot of satellites put in space, and my worry is there is no traffic jam and accidents in terms of collision for these satellites, and also frequency and signal interfere since they send EMRs. Yeah, so there's a lot of talk about the space junk that's out there. And, I was reading an article that different countries have different control over certain areas in space. I didn't know that, but it actually is there. So let's hope that, the people higher up in these different agencies are taking cognizance of that fact. And I do know that a lot of talk around space junk and all the worries about the traffic jams that you are talking about, etc. So yes, it's something to take note of and to be wary of. And especially with all the little CubeSats that are also going out, there's lots of worry and concern about that. But let's hope that the powers that be are able to look at that and help us overcome that issue as well. I see Mariah has put a reminder here. Can I please ask you all to turn on your cameras? Mariah requires a picture for our administrative and funding purposes, so that we could see that there were real people that attended the session and not just computers. Oh, it's lovely to see all of you. So Mariah, you're going to take a picture for us. Maybe I should also turn on my screen, hey?
Yes, I will try from this end. You can also try from that end.
Sure, I will also try from my end. I think we've got almost a complete screen here. I think some people, looks like some people are busy with field work and listening to us, which is very nice. I'm glad that you can make the time. I mean, there's time differences, and people are so busy. I know a lot of you are working on your research from what I gather. A lot of you are lecturers, so you're busy with exams, and some of you are very busy out in the field as well. So we're really happy that you've made the time to join us. And we're hoping that with this initial pilot online course, we can improve it and make it something that, you know, people can register for, and we can make this a bigger way of moving forward and learning. So as I said, we're going to have a few teething issues here, but let's hope that it can become quite a successful one. So thank you so much. I've taken the picture, Mariah. Have you gotten it as well? All right. So I'm not going to let you off that easy. I'm known to be quite the captain in terms of my teaching. My students know me to be quite the captain. So you have a task, a small task. And I'm going to quickly share that screen again so that you can see your task. Let's just go to the bottom. All right, so the assignment task that you have is a very simple one. You're going to write a one-page summary of any journal article where either satellite-based evaporation, rainfall, soil moisture, vegetation, whatever it is, you're not limited. You're going to write me a one-page summary of a journal article where they have used this type of information for any type of water resources management, decision-making, etc. But the article must be less than 5 years old. So anything between 2017 to 2021. And I really don't want an article where you are the first author. So it must be somebody else's work, okay? And this is due on Thursday, the 18th of November by 11:59 midnight. So I will put this up as an update, a message on the platform, and you will read the question there. The presentation will be uploaded as well. So after the session, I will send this presentation and Mariah or Hope will upload it onto the system and publish it out there for you. I will convert it to PDF so that it makes it smaller to host onto the studio system. And I see I have a question from Cuthbert. You've got your hand up. Taguta, Cuthbert Taguta.
Hey, hello, how are you?
Hi, I'm fine, thanks. How can I help you, Cuthbert? You have a question.
Okay, thank you very much for the wonderful introduction and presentation. My question was, from your experience, what is the smallest geographical scale at which we can, let me say, safely apply remote sensing data? For example, if we are to do hydrological assessments of let's say, rainfall. And then the next question is, how accurate is RS data from your experience?
Okay, so from my experience, let me start. Thank you for the question, first of all, and it makes me very happy and excited to answer the question, because I based my master's study on hydrological modeling for design flood estimation, and I looked at scale issues. So that was, you know, my area of study. And I used the same model, which is the Acura model. So for us in South Africa, we found that, you know, we have our quaternary catchments, which is what, you know, the country has been divided into at the FOT level. Then we went down to quinary catchments, which is a finer spatial scale. And I did a study where I looked at the differences between modeling at the different scales and how they affect us in terms of the stream flow output that we get. And from the work that we did, we found that the best results were HRUs. So HRUs are the hydrological response units. And my HRUs were set up in that they represented a land cover with a particular soil class. So I did my HRUs based on both land cover and soil. So I could have had one sub-catchment, which had 5 different land cover classifications, but it only had 2 different soils. So I would have 10 combinations of land cover and soils information, and then model with that. So in that work, I didn't use satellite rainfall information, satellite rainfall information. But I did, in this little study that I showed you, I actually also looked at a larger scale. So I took one of the subcatchments in its entirety, and I calculated an average satellite-based rainfall estimate. And then I took HRUs and then calculated, using the satellite rainfalls there, and then did the modeling separately. And again, the HRUs performed better in terms of scaling issues. So I guess it depends on your scale. The spatial resolution of your product as well is going to be important. And some of the products, when they are, the spatial scale is much bigger, particularly compared to the catchment, then you'll find that you have 1 pixel covering the entire catchment, whereas previously you could get, various rain gauges driving the different areas in your catchment. It becomes more important, depending if there's altitudinal differences, etc. So there's no one completely correct answer to your question, but definitely for hydrological modeling, from my experiences, I find HRUs give me better results. And even with using the remote sensing data sets, the spatial resolution, what we were doing is we were still adjusting with the rain gauge in some instances. So the rain gauge being using as a sort of bias correction for the satellite gave us much better results when we put it through the hydrological model. At the moment in my PhD, I'm looking at blended products and downscaling the satellite information. I'm looking at TRIM as well as the move to GPM, the iMerge products. And I'm creating a blended product and a downscaling methodology to use within the modeling system, also at different scales. So hopefully when I'm finished my PhD in about 2 years, I'll be able to answer your question fully. And I'll make sure to do, what do they call those? Monte Carlo simulations. What's the word? Uncertainty analysis. And I'll make sure to include an uncertainty analysis, because you're never too certain with this, but I mean, you could do the best you can. Catchments are so unique. You can't just say it's going to work like this here and it's going to work differently in another area. You have to find homogeneous catchments in order to able to, say that this is going to happen overall, etc. And I would like to perform it in various areas to actually come to that type of conclusion. But yeah, I hope I've tried to answer your question.
Yes. Thank you very much for the
There's
clarification.
Plenty of opportunity for research and taking all of this technology forward. Okay, are there any questions about the assignment task? There will be instructions about how you upload it onto the system, etc. And we'll put an update as well. So please keep checking your updates. You can click on updates and you'll be able to look at all of the information that's posted for you. I hope that you are all going to stay on, and definitely the Google Earth Engine session is quite an important one. It's going to make life so much easier, show you some tricks on how to download data and make life easier in terms of being able to actually use the technology appropriately. And next week, our colleagues from UDSM, they'll be introducing you to the GLDAS and QGIS, and that's really excellent technology to be able to use if you're interested in Earth observations and hydrological analysis. So please stay on and keep attending our sessions, and please participate in our course. All right, are there any other questions for me?
No questions.
Okay, so thank you so much. You know, I'm a lecturer, so I can go on talking a hell of a long time. So we rather stop here now. I hope to see many of you come visit us at UKZN. We're a beautiful university. We're very well recognized, and we're very happy to be affiliated with WaterNet and to be able to contribute to capacity building on our continent, right? On our beautiful African continent. All right, so thank you very much. I'm going to end the session, and we'll see you on Thursday at 10 a.m. Johannesburg time, where we will be looking at the Google Earth engine. Thank you very much.
Thank you, Ms. Chetty.
Thank you, Mariah.
Bye.
Bye.
Thank you. Bye.
Bye.